Hi everyone, I present you our latest research, self-adjusting weighted expected improvement for Bayesian optimization. I'm Carolin Benjamins and this was joint work with Elena Raponi, Anja Jankovic, Carola, Doerr and Marius Lindauer. And our motivation in general is that we want to make Bayesian optimization more efficient. And we know that the design and the selection of the components impacts the performance, and that the acquisition function influences the exploration-exploitation trade-off, and that a dynamic choice of the acquisition function can be beneficial and should happen per run. So we asked ourselves, how can we set the exploration-exploitation trade-off based on the current progress? And for this, we look at the acquisition function weighted expected improvement by Doerr et al. It consists of an exploitation term and an exploration term weighted by alpha. And you see that the exploitation term contains the original pi. So depending on alpha, we get different behavior. Alpha equal to 0 is as exploring as possible. Alpha equal to 0.5 recovers EI, and alpha equal to 1 is as exploiting as possible. It's the modulated pi term. So the question transformed to how should we set the general exploration-exploitation trade-off to when and how to adjust alpha. We first look at the when. So we saw that there's a stopping criterion for BO or HPO proposed by Makarova et al. And they stop the optimization process whenever the upper bound regret is below a certain threshold. This is an indicator of progress, this UBR, and looks as follows. So we have the estimated worst case function value of the incumbent minus the estimated lowest function value across the search space. So with this, we estimate how much more progress we can make. And our rule is simple. We adjust alpha whenever this upper bound regret converges, so the gradient is approximately 0. This has the advantage that we don't need to set any threshold. Now the question is how to adjust alpha, and we propose a simple yet effective additive change by delta alpha equal 0.1. So we add or subtract 0.1. And we decide the direction based on the attitude, on the search attitude. And we adjust alpha to the opposite of the current search attitude. The intuition behind it is when the upper bound regret converges, that might mean that we can't make that much progress anymore under the current optimizer settings, so under the current search attitude. So we should adjust into the opposite side, and the rule is also simple. We compare the exploration-exploitation terms, and if the attitude or if the exploration term is bigger than the exploitation term, that means we are exploring and should adjust into the opposite direction and vice versa. Let's check out a simple example or a small example on the BBOB function 20 in 8D. The function looks like that down below, presented in 2D. And we first have the upper bound regret. It goes down in general. It's a little bumpy, so we smooth it also. We check the gradient, and we check whenever the gradient is approximately 0. That means we should adjust something indicated by the gray lines. And we check the gradient proportional to the current scale. Then we can see the resulting alpha schedule. So we see that alpha is first increased and then later on decreased and increased again. And lastly, we see the nice thing that the log regret also decreases. Let's come to the empirical evaluation. So we looked at 2 domains. We ran our evaluations with 10 seeds, and we have the 24 single objective noiseless BBOB functions from the COCO benchmark in 8D with 3 instances. And we have 40 tasks of the HPOBench-ML track where we optimize XGBoost and random forest and so on. And our framework of implementation was SMAC3. So we also compare against baselines. So of course the natural thing is to compare to static alphas, so alpha equal to 0, 0.5 and 1. And also to compare linear increases and decreases from 0 0.5 to 1 and vice versa. And we also, from our previous work, we compare switching from EI to PI after a certain amount of our budget. And finally, we have the Gutmann-Sobester pulse, where we cycle through alpha values indefinitely. And finally, portfolio allocation, where we pull different arms, which are different acquisition functions. So let's check out our BBOB function 20 again, how our baselines and our method works. So SAWEI is indicated by this purple, dark purple line with this marker, and we have all the baselines. And let's first check the log regrets. So SAWEI performs quite well, and also the switching schedules perform quite well and the linear decrease. Looking at the UBR, we see a similar trend is going down, and it's a little bit different per function. But it does not really correlate with the final log regret. And then we see the resulting alpha schedule. So we see here the alpha schedules from the baselines, and here our SAWEI alpha schedule from EI to exploiting and back again to exploring. Let's check out the anytime performance on BBOB. So again, we see our SAWEI method, which performs quite nice throughout all the optimization, and it's later passed by the linear decrease and increase and the switching schedules. But the thing is, for those schedules or for those alpha schedules, we need to know the final budget. If we don't know really how much function evaluations we can spend, SAWEI is a really good choice, and it's good in the beginning up until the end. And on HPOBench, this is even more clearer. So we see that SAWEI has a pretty nice anytime performance. In the beginning, SEB is quite strong, but is not that good later on. And you might have also noticed that the baseline's order has changed. And let's look at this in more detail by comparing SAWEI across domains. So we first look at the search attitude, and we see that on BBOB and on HPOBench we have the opposite search attitudes, or the opposite alpha trajectories discovered by SAWEI or traversed by SAWEI. And also looking at the ranks across the domains for each baseline, we see that SAWEI has the most favorable rank distribution, and that other baselines are pretty strong per domain, but not on both. So SAWEI is a robust default choice. Let's come to the limitations and future work. So SAWEI does not allow jumps and resets of alpha, which might be very beneficial, and the initial value of alpha is always the same. So thinking of the future, we might meta-learn this, or combine this with a meta-learned approach using ELIF features or other time series features regarding the initial value of alpha or resets. And we can, of course, extend our approach to any linear combination of acquisition functions. And we would like to investigate the potential of a reinforcement learning approach. And in the long term, we would like to adjust all BO components on the fly. Let's sum up SAWEI in a nutshell. So the motivation is that we want to self-adjust the exploration-exploitation trade-off on the fly per run in Bayesian optimization. And our method SAWEI modifies the weight of the weighted expected improvement acquisition function when the upper bound regret converges and opposite to the current search attitude. And properties and insights are SAWEI self-adjusts per run and discovers different alpha trajectories per domain, and it's a robust default choice. And finally, SAWEI is also budget agnostic and computationally cheap. If you want to know more, check out our repo and our paper, and we would be very happy if you come talk to us at the conference. So see you there.